Okay, last week we have discussed the determination of the transmission line load. We have introduced the standing wave ratio measurement, so that according to the measurement result, you can determine the property of your transmission line termination. So in that measurement, we need to determine three properties. The first one is the standing wave ratio, which is related to the magnitude of the reflection coefficient. So as shown in equation 7.29, you can see that originally in 7.26, the standing wave ratio can be expressed in terms of the magnitude of the reflection coefficient. Therefore, the reflection coefficient magnitude, as shown in 7.29, can be expressed in terms of standing wave ratio, which is the ratio of SWR minus 1 divided by SWR plus 1. The second and third property that we acquire from the measurement is T minimum, the distance on the transmission line to reach its first voltage minimum, and the wavelength, which can be determined by looking at the voltage variation on the transmission line and the distance between two minimum or two maximums on the transmission line is about half a wavelength. So if you times the distance by 2, you can get the wavelength of the transmission line at that frequency. So in the second and the third information we acquire from the SWR measurements are the T minimum and lambda. So here's the relation we need to use in 7.30. So originally, theta minus 2 times beta times T minimum is minus pi. Because we are choosing the voltage minimum, so the phase when you reach voltage minimum on the transmission line equals to 180 degrees, which equals to minus pi. And theta is the angle of your reflection coefficient. So from the SWR measurement above, we know the magnitude of the reflection coefficient gamma, but we don't know the phase of the reflection coefficient. That's the reason why you need to find out the T minimum distance, so that you can use this equation to find the theta, the phase information of the reflection coefficient. By massaging this equation a little bit, you end up with equation 7.30. Theta equals to 4 pi times T minimum divided by lambda. So the two parameters circled with red dashed line are the information we acquire from the SWR measurement. So substitute the measure value in equation 7.30. You will get the angle of your reflection coefficient gamma. Why do we need gamma? The ultimate goal is to find ZR, as shown in equation 7.31. The ultimate goal is to find out the input impedance, the impedance of the termination. So ZR is the impedance of the termination, and it can be shown as a composition of the characteristic impedance times 1 plus gamma R divided by 1 minus gamma R. So you need to know the magnitude and the phase of gamma R so that you can find out the impedance, input impedance of the termination. And in fact, we are not satisfied about knowing the termination property, ZR. We are more interested about the, well, let me look forward. So ZR, R is the impedance at the load. And in fact, we are more interested about input impedance at a certain location on the transmission line. We want to know not only the termination of the transmission line, we want to know the equivalent input impedance anywhere on the transmission line, which, as you can see here, can be composed by characteristic impedance and reflection coefficient at that location. Note that this is gamma D, which is the reflection coefficient at a certain distance away from the low D. So it's not gamma R as we derive from the SWR measurement, but gamma D is kind of a transform of gamma R with. So as you can see from the red box, gamma D is the product of gamma R, the reflection coefficient at the low, times exponential minus J 2 beta D. What is the implication of this exponential term? The significance of the exponential term is that represents the propagation delay, in particular round-trip propagation delay. That's the reason why you have 2 over there. The round-trip propagation delay accumulated from D to the low and back. All right, so go back to our measurement example. So here we'd like to introduce you the equipment you need to perform the SWR measurement. So in example 7.2 in your textbook, it shows a picture of the measurement equipment you can have with the you can use to perform the SWR measurement. So here you have oscilloscope, which records the voltage signal in the transmission line. You have a waveguide, a rectangular waveguide with a slot line cut in the middle. The slot line is cut in the middle so that there is no radiation escape or emitted from the slotted line. The reason why it cannot radiate is because of the boundary condition in the waveguide structure. So if you cut in the middle, there will be no transverse electrical field appear on the slot. Therefore, there will be no radiation emitted, radiates from the slot. However, if you put a voltage probe, a high impedance voltage probe, a high impedance electrical field probe inside the waveguide, you can measure the voltage with certain conversion, equation. You can have the voltage, the field, the electrical field intensity within the waveguide. And you know that there, at the right end of the transmission line of the waveguide, you can exchange for different types of termination. You can attach it with a short, or leave it as open, or attach it with a match load or attenuator. Okay, and on the left-hand side, you have a signal generator, which provides a sinusoidal signal into the radio RF sinusoidal signal within the waveguide, so that you have electromagnetic wave going back and forth within the waveguide. So here to the right is a picture. To the right is a picture. So as you can see, you can use a coaxial cable attached on the top of the probe, of the electrical field probe. And you can see there are two connectors. We call it flanges. So a flange connector on the right and left. To the left, you can connect it to the signal generator, and to the right, you can connect it with different types of termination. All right, then here are the description about example 7.2. With one of the minima marked on the reference point. I should begin with here. So the first step is attach a short termination on the waveguide. So what is the purpose of this step? Well, the purpose of this step is to get a reference point for your following measurements. Why? Because on the blackboard, when we draw the transmission line, and we have a short termination on the right hand side, and we know there will be a complete standing wave. So you look at the voltage plots, that will be a zero, a null, for your short termination. And on the blackboard, you can move your probe any way you want. You can start with t equal to 0. However, if you take a look at the picture, there's a limit that how far your probe can move to the right, right? So it cannot reach this point. So for actual devices, you cannot. There's some certain limitations that your probe can be moved freely. So for example, this region, you cannot move your probe into this region. So you won't be able to determine the location of zero voltage. Fortunately, the voltage null appears periodically with a short termination. And we know that for every half a wavelength, you will encounter a voltage minimum. So the reason for your first step, that is, connected the waveguide with a short, is to provide you a location for your measurement reference. So once you attach the short on the right, you move your probe. You move your probe at a few locations and examine the oscilloscope and look and check up with the oscilloscope to see if you can find a zero voltage location, and that can be your new reference. That will be your reference point. Okay, because we know that this place is separated from the load location with half a wavelength, or one wavelength, or 1.5 wavelengths. Okay. Anyway, it's a multiple of the half wavelengths. So the next step is connect the short. It is to replace the short with your unknown load, ZR. And as you can expect, the complete standing wave phenomenon shall go away if the attached load is not short or not on open or not in fully reactive termination. As long as it has some resistance, you won't be able to have voltage zero on this line. So, but what can you do is moving the probe back and forth and check up the location for maximum voltage and minimum voltage, and record the voltage you find on the oscilloscope. So for example, in this example, the maximum voltage is about 3 times of the minimum voltage. So you have a standing wave ratio of 3. So once you have the standing wave ratio, which is 3 in this case, you can calculate the magnitude of your reflection coefficient using the equation above. So 3 minus 1 divided by 3 plus 1, you end up with 0.5. So the magnitude of the reflection coefficient is 0.5. And we also know by moving the probe back and forth, we see the minimum, the successive voltage minimum. Or you can do that when you attach the waveguide with a short, which provides you a voltage 0. Now you check up the distance between 2 voltage 0. And in this case, it's 20 centimeter. So you know half wavelength in this frequency is 20, in this waveguide is 20 centimeter. So one wavelength will be 40 centimeter. And now, this sentence is the most tricky part of this example. So be careful. So you need to keep up with me about the meaning of this sentence. Because the voltage minimum shift toward the load. What do you mean, shift toward the load? On the transmission line, you have 2 ends. The right end is the load. The left end is what? Generator. Okay? To the left is generator. To the right is the load. So it actually find in this experiment, the author tells us that the voltage minimum is actually found in the right of the reference point, which has a distance of 5.8 centimeter. The voltage minimum shift toward the low. Toward the low means toward the right. To the right, from the reference point is 5.8 centimeter. Therefore, the actual T minimum value should be 20 minus 5.8, which ends up as 14.2 centimeter. Okay, so if you observe your reflection coefficient, again, tomorrow we will introduce another tool referred as the Smith chart. You will have at least 2 problems in the final with Smith chart. Okay, if you take a look at the sample final exams, you see there are at least 2 questions will be conducted using Smith chart. Okay, so you need to be acquainted with the Smith chart tool. The Smith chart, which appear as a circle on the circle Smith chart.我每年都要画那个 Smith chart， 越画越高兴。那明天我们会进行一个法会叫做除魅仪式就是要说让你看清楚 Smith chart 的真面目那我们今天先透露一下Smith chart 的真面目是什么？不要被那些圆线圆圈圈圆弧线所迷惑因为那个都是假象。Smith chart 真正的意义就是 reflection coefficient. The true meaning of Smith chart is the reflection coefficient on complex plane. So if you so the large circle of the Smith chart is the unit circle, which is the circle of magnitude equals to 1. So the reflection coefficient for all possible passive termination will be locating within the unit circle. That is to say, the magnitude of the reflection coefficient for any passive component will be smaller or equal to 1. So the reflection coefficient appear on the complex plane will be located within the unit circle. For example,在你们学 Wen-Jiao 之前，或许这个除魅仪式这样来做会比较简单一点。请问这个白点的值是多少？白点的大小是多少？ 0.5 啊，对不对？同意吗？白点的magnitude 是 0.5， 白点的角度是多少？45度，对啊。那这一点呢？大小是1，上角呢？225度，好。这里呢？0.2、0.3 ，whatever， 90度，好吧？会了哈，啊，这个是 Wen-Jiao 的本质啦。我们看到的点都是 reflection coefficient， 啊，那一条那些线看起来很，你就想象你是唐僧进了女儿国，好不好？哈，那些蜘蛛精画的那些丝就是这些圆弧线呢，好不好？哦，那迷惑你的，好不好？我说他们也是有用的，然后是方便你把根据阻抗的时虚部，把 reflection coefficient 的那个点画出来。好，所以 Wen-Jiao 它本质上就是一个 transformation， transforming impedance into reflection coefficient. Okay, so well, if we go back to the reflection coefficient will rotate clockwise as it moves from right to left. Now, if the points on if the reflection coefficient on complex plane moves from right to left on the transmission line, it shall follow a locus clockwise. On the other hand, if it moves counterclockwise, then it's moved from left to right. So, in this description, we know that the d minimum, the distance that we found for this termination is 5.8 centimeters to the right of the reference point. So in other words, you move 5.8 centimeters counterclockwise to reach the voltage minimum location. And because the distance of one circle, which is half a wavelength, is 20 centimeters. So the actual D minimum you have is 14.2 centimeters. So you know, so what is the reflection coefficient? What is the reflection coefficient at that point? Well, the magnitude is 0.5. How about the phase? 70 degrees something, right? So that should close to the result, about 70 degrees. So if it's in the first quadrant, that will be 0 to 90 degrees. Second quadrant, 90 to 180, so on and so forth. So if we substitute this relationship, we find out the angle theta, which is expressed in terms of radians. Okay, so for a full circle, you have 2 pi radians. So in this case, the theta angle will be 0.42 pi, 0.42 pi, which is a little bit less than half pi. So if it is 0.5 pi, where is the location? No, that would be on the imaginary axis. Okay, if it's pi, then you will have, then the termination will be found in this direction. Okay, so with the measurement result, you can find out both the magnitude and the angle of the reflection coefficient. So do we know the complete description about the termination yet? No, we only know the reflection coefficient, magnitude, and phase of the termination. We haven't found out the ZR, the termination property, the impedance of the termination yet. But it's a piece of cake. You can find out ZR using this equation, which is the product of characteristic impedance times 1 plus gamma R divided by 1 minus gamma R. So the technique you need to master is the technique using your calculator, okay, to change numbers between polar form and real and imaginary number. Okay, you need to know how to convert complex number into magnitude and phase, and convert a number expressed in terms of magnitude and phase into real and imaginary part. Okay, so you begin by using the representation of reflection coefficient, and you see it's changing into real and imaginary part on denominator and numerator, and then it converts back to magnitude and phase, so that you can execute the division. You can find out that you can execute the division more easily. So you just divided the magnitude and do the subtraction over the angle, and you end up with an input impedance of 60 ohm with 52 degree, which can also be expressed as 37 plus J 48. So you need to master this calculation technique. All right. And okay, so that's I try to explain why the D minimum value is 14.2 graphically using this graph. So well, I guess you can check up with this yourself, because the limit on because of the limit in the moving range of the probe. So you can not get the D minimum directly, but you can find out the D minimum value indirectly using a reference point. Okay. So if, for example, the reference, the minimum is found here, the reference point is found with short termination measurement. All right, so the next thing, okay, so the very next thing is to find out the impedance somewhere on the transmission line. For example, we want to know the reflection coefficient, or we want to know the Z, the impedance Z at a position D. Then, by definition, it's the ratio of total voltage over total current, and that can be expressed in terms of reflection coefficient at that position D. So that would be gamma D. And I already pointed out gamma D is a translation of gamma R with a propagation distance. So the translation will be exponential minus J times 2 beta D. okay, with the propagation delay, huh? So once you find out the reflection coefficient at the location D, that's gamma D, you can synthesize the input impedance at location D as this, okay? So in the previous page, you have found the gamma R. So once you know the distance D, you use gamma R times exponential minus J2 pi beta D. You will find out the required required impedance at position D. And before we leave this example, I would like to point out a few things to check about this measurement. At the location of a voltage maximum, where can you find a voltage maximum? Well, where is the position of voltage maximum? Over here, right? And according to the reflection coefficient, here you have voltage minimum. So where is the location of voltage maximum? On the right hand side. Huh. Well, I didn't draw this quite correctly. Huh? Well, for a more general case is this. Why do I draw this white circle? This means the reflection coefficient is smaller than 1. It's a more general case. So if you have some resistive load or resistance with some reactance, you will end up with a reflection coefficient smaller than 1. But it will be a circle on the complex plane. And actually this circle will be introduced as SWR circle, constant SWR circle. For lossless transmission line, once the termination is determined, the reflection coefficient magnitude is fixed. So no matter it goes to anywhere on the transmission line, the magnitude of the reflection coefficient will be the same for a lossless transmission line. So the locus of all reflection coefficient shall form a circle on the complex plane. And this is referred as the constant SWR circle. On the constant SWR circle, the right end of the constant SWR circle, you will have a voltage maximum. And on the other hand, the left-hand side of the constant SWR circle, you will find the voltage minimum. And voltage maximum will be accompanied with current minimum. And the voltage minimum will accompany with voltage maximum, as we discussed last week. As a result, and note that both voltage maximum and current minimum are real number because they are found at this position. So the voltage is real, is a pure real number, the current is a pure real number. The division of the two, that is the impedance at that position, will be a pure real number as well. Will be a pure real number as well. So you will have a Z, I don't know how to fix that. Z what? Well, it actually has a relation over here. The impedance you found here will be the product of Z sub 0, your characteristic impedance, times SWR value. Oh. if you divide maximum voltage with minimum current, you end up with a product of characteristic impedance times the SWR value. On the other hand, on the other side, the Z, so that will be actually the maximum impedance. That's the maximum real impedance you can find with this termination on the constant SWR circle. On the other hand, on the other side, you will find the minimum, the smaller real impedance, which is the division of voltage minimum with current maximum. So that will end up a real number, but it's a number smaller than the maximum impedance. And it's actually Z sub 0 characteristic impedance over SWR. Okay? And you can find out another interesting relationship is Z max times Z minimum will be what? Square of characteristic impedance. In fact, for any two positions that are accurate, that is placed oppositely on the constant SWR circle. For example, this is Z. ZA and ZB. Okay? ZA, as you can see, is a complex number. No, it's not on the real axis. ZB is a complex number as well. But because they are on the opposite ends of the constant SWR circle, the product of ZA and ZB will equal to the square of Z sub 0 as well. So that's an interesting relationship you can find with termination on the transmission line. This is, and you need to remember that the distance to move ZA to ZB is how far? A quarter wavelength. Okay? A full circle is half a wavelength. Half circle is a quarter wavelength. So in the design of a microwave circuit, the quarter wavelength principle is kind of important because many components are invented or designed using this principle. Okay? So you see, on the right end of the real axis, you find the maximum voltage, minimum current, so you have the largest impedance, which is Z sub 0 times SWR. On the other end, you have voltage minimum and current maximum, and the resulting impedance, which is a pure real number, so it's returned as marked as R minimum because it's purely real. And it's the product, well, it's not a product, it's Z sub 0 equals to Z sub 0 divided by SWR. Okay. So, at any place else, the impedance is a complex number. And if you take the product of R maximum and R minimum, you will end up with Z sub 0 to the square. And this quarter wavelength principle is valid for any place, for any 2 points on the opposite side, opposite ends of the constant SWR circle, because the relationship. So here is the derivation. For any point on the transmission line, say the distance is D, For any point that is a quarter wavelength away from D, that is D plus or minus lambda over 4. If you check up with the expression of their impedance, that is Z sub 0 times 1 plus gamma D divided by 1 minus gamma D. For the other end, that will be D plus and minus a quarter wavelength. And we know that the propagation delay of a quarter wavelength will be this: exponential minus or plus J2 beta lambda over 4. If you substitute beta with 2 pi over lambda, this will end up with plus or minus J pi. Exponential J pi will be minus 1. Plus J exponential plus J pi will be minus 1 as well. So on the denominator and numerator, it will be changed into minus and plus. So you can see here, the things in the middle parentheses cancel each other. So you end up with Z sub 0 to the square, as you can see from equation 7.33. All right, so finally, we can find out the equivalent input impedance at a distance away from the load. So finally, let's check up with another example, a transmission line. So here we have the characteristic impedance is 50 ohm. The length is 0.725 lambda. You have a voltage source of 100 volts in magnitude and 0 degree in phase. Note that this is a sinusoidal source, a generator of sinusoidal signal. We didn't specify the frequency, but that doesn't matter for this problem, because everything are measured in terms of wavelengths. So we don't have to specify the frequency. The internal impedance of the generator is 10 plus J10. And the termination is 30 plus J40 ohm. So we need to do the following. We need to calculate the reflection coefficient at the load, the reflection coefficient at the input end, the impedance Z at the input end, and we can use the equivalent impedance, equivalent input impedance to find out the voltage and currents in supply to the transmission line. And finally, we can calculate the time average power delivered by the source. So, of course, you need to follow this derivation at home. So first thing is compute the reflection coefficient, which is which is quite regular, okay? There's ZR minus Z sub 0 divided by ZR plus Z sub 0. That will be 0.5, and the angle is 90 degrees. And you need to translate this reflection coefficient from the right end to the left end, which is a distance of 0.725 lambda. So you have gamma R over here, you times exponential minus J2 beta L. L is 0.725 lambda. And for your convenience, we can read it in terms of degree instead of radians. That will be minus 162 degrees. And because you have a 90 degree here, so you have a total of minus 72 degrees. So this is the equivalent input impedance at the left end. Note that the magnitude on the left hand is 0.5. The magnitude of the reflection coefficient at the termination is 0.5 as well. So they have the same SWR value, but the phase is different due to the translation on the transmission line. Then you can calculate the input impedance using the reflection coefficient at the left hand, which is about 40 minus J50. So the input impedance is used with ZG, the generator internal impedance, to find out the current supplied into the transmission line. The voltage is 100 volts, 0 degree, and the denominator is the summation of the two, and you can find out the current will be 1.55 amp with a phase of 40 degree. Okay. Next, we need to find out the voltage over here. The voltage over here is 100, but well, and it can be found by the product of the current and the input impedance. So the voltage at the left end will be 100 volts with minus 12 degree. So the very last thing is do the product of the voltage and the current. Note that you need to apply the complex conjugate to either current or voltage 其中之一要乘上它们的那个 complex conjugate. Okay? Then you and times take the real part and times 1/2, and you end up with the power delivered by the generator, which is 48 watt in this case. All right, and the last two slides of this set are the definition of normalized line impedance. That is, divide the impedance on the transmission line with the characteristic impedance. So this is referred as normalized impedance, which is useful in our next section, section 7.3, when we introduce the method of Smith chart. In Smith chart, we are more comfortably working with normalized impedance and normalized admittance 正规化的阻抗跟正规化的导纳。那它这个定义其实很简单，就是除上 characteristic impedance 跟 characteristic admittance 然后你的那个反射系数还有反射系数的表示式也是可以用正规化的那个阻抗或者正规化的导纳来去显示所以这个来自己看一下就好。好。